You've tuned into the Sleep Enigma, where we embark on tranquil journeys through the vast cosmos, the currents of time, and the boundless wonders of the natural world, one gentle thought at a time. Tonight, we are setting sail on an extraordinary voyage back into Earth's most profound and ancient past, to an era so distant that our entire planet may have been utterly consumed by an impenetrable shroud of ice. This isn't merely a scientific concept. It's a gripping narrative of colossal glaciers carving continents, of ancient snowstorms blanketing the globe, and of a world that teetered precariously on the brink of becoming a singular, frozen marble, drifting in silent majesty through the cold vacuum of space. Before we metaphorically don our warmest parkas and venture into the exhilarating chill, I extend a heartfelt invitation to you. Whether you find yourself enveloped in the profound stillness of the dead of night, or perhaps just settling down after a comforting dinner, my sincere hope is that this journey offers you a quiet companionship, a gentle presence in your hours of rest or contemplation. If you find true enjoyment in this tranquil expedition through the annals of time, please consider extending a simple gesture, tapping that like button, or perhaps even subscribing to the channel. Such actions, small as they may seem, genuinely help our little community grow, ensuring you'll never miss our next sleepy exploration into the mysteries of our universe. A small but important heads up, dear listener. I've poured my utmost effort into crafting this video to be as calm and profoundly relaxing as humanly possible. In my earnest attempt to be informative yet soothing, I may have inadvertently made it just a little too interesting, perhaps even captivating. So if you do find yourself managing to stay awake, defying the gentle lull of my voice, my hope is that it's because you are genuinely discovering something truly fascinating, something that sparks your curious mind. And if, by some happy accident, you happen to drift off into slumber halfway through, well, that's perfectly, wonderfully all right. The ancient glaciers, in their timeless patience, will still be here, waiting for you when you awaken. The Enigma of the Ice Age, Earth's Rhythmic, Freeze and Thaw, a deep dive into planetary history and its enduring legacy. So let's begin. What precisely is an ice age? It's a term deeply ingrained in our collective consciousness, often evoked by childhood documentaries featuring clumsy woolly mammoths precariously slipping on sheets of ice, or whimsical cartoons depicting cavemen adorned in surprisingly well-tailored furs. But beneath these frosty, often comedic portrayals lies a surprisingly nuanced and profoundly captivating scientific concept. An ice age isn't simply an exceptionally long winter, nor is it merely a particularly snowy decade. Instead, it is a prolonged geological epoch, a vast span that in some cases stretches for millions of years, during which Earth's global climate experiences a sustained cooling trend. This cooling becomes sufficiently frigid for expansive ice sheets and colossal glaciers to form and persistently remain, especially concentrated at our planet's poles and higher latitudes. This isn't just about localized snowfall, it's about a fundamental long-term shift in the planet's energy balance and hydrological cycle, driven by complex interactions between the atmosphere, oceans, land, and even the cosmos. And, to an astonishing degree, we are in fact living in one right now. Yes, you heard that correctly. Despite your radiant summer tan and the conspicuous absence of saber-toothed tigers roaming free in your local park, we are, from a scientific standpoint, still immersed within an ice age. More specifically, we are presently nestled within an interglacial period, a comparatively warmer phase that is itself part of a much grander, more extensive ice age that began approximately 2.6 million years ago, known as the Quaternary Ice Age. This interglacial, the Holocene epoch, has provided the stable climate conditions crucial for the rise and flourishing of human civilization, allowing for the development of agriculture, permanent settlements, and complex societies. So the next time someone confidently declares that humanity has left the Ice Age behind, you can, with a gentle, knowing smile and perhaps a raised eyebrow, softly interject, "Actually, my friend, we're simply enjoying a temporary thaw, a brief warm breath within a much longer, colder geological exhalation, a pause in the long cycle of planetary refrigeration." This perspective highlights the cyclical nature of Earth's climate and places our current warm period within a much larger, colder context. To truly grasp the intricate dance of Earth's climate, let's first establish the foundational principles. Our planet's climate is never static. It is in a perpetual state of flux, undergoing continuous transformations that can range from exquisitely subtle to breathtakingly dramatic. These monumental changes unfold across a vast spectrum of timescales, from a mere few years, influenced by events such as explosive volcanic eruptions, which can temporarily cool the planet by injecting light-reflecting sulfur aerosols into the stratosphere, blocking sunlight, or dynamic shifts in ocean currents, like the El Niño Southern Oscillation, cycles which redistribute heat in the Pacific Ocean and influence global weather patterns to tens of thousands or even millions of years. These longer-term shifts are driven by subtle yet powerful orbital wobbles, Milankovitch cycles, cataclysmic tectonic shifts, continental drift and mountain building, and fluctuating levels of greenhouse gases in the atmosphere, influenced by both geological processes like volcanism and weathering, and biological processes like the carbon cycle and changes in vegetation cover. Ice ages represent one of the grandest, most epic, and enduring of these long-term climatic shifts. They are akin to the planet's deep rhythmic breaths, alternating majestically between profound cold, glacial periods or glacial maxima, and rejuvenating warmth, interglacial periods. The quintessential hallmark of an ice age is the pervasive presence of truly gigantic ice sheets sprawling relentlessly across continental land masses. We aren't speaking here of a few ephemeral snowstorms or a mere dusting of seasonal frost, but rather of vast, ceaselessly grinding, almost mind-bendingly heavy rivers of solid ice that extend across immense portions of the globe, sometimes covering millions of square kilometers. Imagine ice several kilometers thick, e.g., the Laurentide ice sheet over North America was up to 3 to 4 kilometers thick in places, comparable to the height of a small mountain range, exerting immense pressure on the crust, even causing the land beneath to depress, a phenomenon known as isostatic depression. This immense pressure slowly but powerfully reshapes mountains and valleys, carving out spectacular landforms like fjords, deep U-shaped valleys now flooded by the sea, common in Norway, Greenland, New Zealand, and coastal British Columbia. Streamlined hills called drumlins, elongated teardrop-shaped hills of glacial till, and serpentine ridges of sediment called eskers, long winding ridges of sand and gravel deposited by meltwater streams flowing within or beneath a glacier. These aren't just frozen patches, they are dynamic forces of geological change, capable of sculpting entire landscapes, scraping away bedrock, and depositing vast quantities of unsorted sediment as till, a heterogeneous mixture of clay, silt, sand, gravel, and boulders, which forms distinct geological layers that provide invaluable clues to past glaciations and the direction of ice flow. During the zenith of the last glacial period, specifically the last glacial maximum, LGM, which occurred approximately 20,000 years ago, colossal glaciers blanketed vast swathes of the northern hemisphere, North America extending as far south as present-day Illinois, Ohio, Pennsylvania, and New York, reaching the latitude of New York City, Europe covering much of Scandinavia, the British Isles, Iceland, and northern Germany, extending into Poland and parts of Russia, and Asia, including large parts of Izu, Siberia, and the Tibetan Plateau. In the southern hemisphere, smaller but still significant ice sheets expanded over Patagonia, New Zealand, and parts of Tasmania. The sheer volume of water locked up in these immense ice sheets had dramatic consequences for global sea levels. They plummeted to astonishing depths, dropping over 100 meters lower than they are today. A dramatic recession that unveiled ancient land bridges connecting continents, like Beringia, the vast land bridge that connected Asia and North America, across the Bering Strait, allowing early humans to migrate to the Americas, and land bridges connecting Southeast Asian islands like Sunda and Sahul, facilitating human migration to Australia and New Guinea. This lower sea level fundamentally reshaped the migratory pathways of both animals and early human populations across the Earth, influencing their distribution and cultural development. The exposed continental shelves added significant land area to the continents themselves, which in turn influenced atmospheric circulation patterns, regional climates, e.g., creating vast dry plains, and the distribution of biodiversity, creating entirely new terrestrial environments and altering marine ecosystems. But here is where the narrative delves into more technical intricacies. Even within the frigid embrace of an ice age, the global climate naturally oscillates between intensely colder glacial periods, or glacials, sometimes referred to as ice ages in the popular lexicon, though technically they are parts of an ice age, and significantly warmer interglacial periods, like the Holocene epoch, which we are currently in, spanning the last 11,700 years. Envision it as a natural, planetary pulse, a recurring rhythm of freeze-thaw, freeze-thaw. These cyclical shifts, spanning tens of thousands of years, are meticulously propelled by a synergistic blend of cosmic nudges, Milankovitch cycles, and intricate planetary feedback systems, like ice albedo feedback, carbon cycle dynamics, and ocean circulation changes. During glacial periods, immense ice sheets expand their dominion, their frosty tendrils reaching further, and global sea levels noticeably recede as vast quantities of water are locked away in ice. Atmospheric CO2 levels also tend to be much lower during glacial periods, often around 180-200 parts per million, ppm, significantly below pre-industrial levels of around 280 ppm. This lower CO2 contributes to the colder climate and is also a consequence of increased oceanic uptake and reduced biological activity on land. Conversely, during interglacials, those colossal ice sheets begin their slow, graceful retreat. Vast volumes of meltwater are released back into the oceans, and the world experiences a notable warming, much like the pleasant conditions we are currently experiencing. These interglacial periods are crucial for biological diversity, allowing ecosystems to recover and expand into newly exposed or thawed territories, leading to periods of significant speciation, migration, and the flourishing of complex life, including the rise of human civilization with its associated technological and societal advancements. To date, Earth has, throughout its venerable 4.5 billion-year history, endured at least 5 major, well-documented ice ages. The earliest definitively known one occurred over 2 billion years ago, during a primordial time when life on Earth was still predominantly microscopic and, fortunately, blissfully unconcerned with such modern conveniences as snow boots or central heating. This ancient ice age, known as the Huronian glaciation, approximately 2.4 to 2.1 billion years ago, is thought to have been triggered by the Great Oxidation Event, when nascent photosynthetic organisms, like cyanobacteria, began to produce oxygen, which reacted with and consumed methane, a potent greenhouse gas in the atmosphere, leading to a profound and protracted global cooling. This was likely one of the longest and most intense glaciations in Earth's history, possibly even rivaling the later Snowball Earth events. Other major ice ages include the Cryogenian, which we'll discuss in detail, around 635 million years, ergo, the Andean-Saharan, approximately 420 million years ago, a relatively short but intense ice age during the Ordovician and Silurian periods, likely linked to the rise of land plants and their impact on atmospheric CO2, and the Karoo, approximately 260 million years ago, occurring during the late Paleozoic era, often referred to as the Permo-Carboniferous Ice Age, linked to the formation of the supercontinent Pangaea and massive coal swamp forests. The most recent and extensively studied is the Quaternary Ice Age, which commenced its long reign approximately 2.6 million years ago, and remarkably continues its influence to this very day. It is within this most recent icy epoch that the human story truly begins to unfold, our species emerging and adapting within its fluctuating embrace, leading to key evolutionary pressures and migrations that shaped human history. Our very ability to adapt to such profound climatic shifts, developing crucial technologies like fire, clothing, shelter, and sophisticated hunting and food storage strategies, has been a hallmark of our survival and expansion across the globe, allowing us to thrive in environments that would have been otherwise uninhabitable. The drivers of global chill, a symphony of planetary forces and feedback loops, an exhaustive analysis of climate regulators. However, ice ages aren't random, chaotic occurrences. They are meticulously triggered and precisely shaped by a complex interplay of various interconnected factors, each playing a crucial role in tilting the Earth's delicate climate balance. Understanding these drivers requires appreciating the deep interconnectedness of Earth's systems. One of the dominant players is the fluctuating concentration of carbon dioxide, CO2, and other powerful greenhouse gases like methane, CH4, and nitrous oxide, N2O, in the atmosphere. These gases act like a thermal blanket, allowing visible light from the sun to pass through to the Earth's surface, but efficiently trapping outgoing infrared radiation, heat, from the Earth's surface, preventing it from escaping into space. This phenomenon is known as the greenhouse effect. Without any greenhouse gases, Earth's average temperature would be a frigid 18 degrees Celsius, 0 degrees Celsius, making it uninhabitable. So, when their atmospheric levels dip low enough, either through geological processes like increased chemical weathering of rocks, which consumes CO2, or biological changes like massive burial of organic carbon in sediments during periods of high biological productivity, effectively removing carbon from the active atmospheric cycle, the planet inexorably begins its slow, steady descent into cooling as less heat is retained. This process can be exceptionally slow, unfolding over millions of years as the Earth's deep carbon cycle, the long-term geological cycle of carbon, adjusts. Yet greenhouse gases represent only a single, albeit crucial, piece of this intricate puzzle. Their fluctuations are often both drivers and consequences of other climate changes. The very shape of Earth's orbit around the Sun also exerts a profound and undeniable influence. Our planet's orbit wobbles subtly over vast stretches of time, tilting, stretching, and precessing in highly predictable cycles, collectively known as Milankovitch cycles. These slow, astronomical shifts precisely affect how the Sun's energy, or insolation, is distributed across the planet's surface, particularly in the critical polar regions. If the timing of these celestial alignments is just right, a delicate cosmic dance, they can decisively tip the climate balance toward widespread glaciation or, conversely, a welcome, life-giving thaw. They act as the pacemakers for the glacial interglacial cycles within an overall ice age, providing the subtle nudges that Earth's climate system then amplifies through internal feedback mechanisms. Then there is the monumental and often overlooked role of the continents themselves, a key player in plate tectonics. Over truly vast geological timescales, continents drift majestically across the globe, like colossal, lazy icebergs, propelled by unseen forces deep within the Earth's mantle through the process of mantle convection, where heat from the Earth's core drives slow currents of semi-molten rock in the asthenosphere. When immense land masses migrate towards the poles, e.g. Antarctica moving to the South Pole or North America moving into higher latitudes, it provides ample surface area for towering ice sheets to burgeon and expand. This is a critical geographical prerequisite for major glaciation, as ice sheets require a stable landmass on which to grow and persist. Without large landmasses at high latitudes, ice cannot accumulate on a continental scale, even if temperatures are cold enough. Conversely, if all continents are clustered around the equator, it makes widespread glaciation less likely, as there's no solid ground at the cold poles for ice to anchor and grow upon. Furthermore, the configuration of continents directly influences ocean currents, which are, in essence, the intricate arteries of the global climate system. These currents, driven by wind, temperature, salinity differences, thermohaline circulation, or the global conveyor belt, and the Coriolis effect, diligently carry heat from the equator towards the poles and play a crucial role in balancing temperature differences across the entire globe, moderating climates worldwide and influencing regional precipitation. However, they do not simply flow wherever they please. They are meticulously shaped and steered by the arrangement of the continents and the seafloor topography. When continents migrate, they fundamentally alter the shape and depth of the ocean basins, which in turn precisely reshapes the direction, speed, and intensity of these vital currents. A seemingly minor shift in continental position can redirect warm water away from the poles, preventing it from reaching and melting existing ice, or conversely, trap frigid water in deep basins, both of which can unleash dramatic and far-reaching impacts on the global climate. For instance, the formation of land bridges like the Isthmus of Panama, which closed around 3 to 4 million years ago and created a complete barrier between the Pacific and Atlantic Oceans. This event significantly altered Atlantic Ocean circulation, intensifying the Gulf Stream, a warm ocean current flowing from the Gulf of Mexico towards Europe and the Arctic, and perhaps increasing moisture transport to higher latitudes in North America and Eurasia, providing the necessary snowfall for glaciation in the Northern Hemisphere, thus potentially contributing to the onset of the Quaternary Ice Age by delivering moisture to high latitudes where it could fall as snow and accumulate. Conversely, the opening of new seaways like the Drake Passage between South America and Antarctica can allow cold water to circulate freely around polar landmasses, enhancing their isolation and promoting glaciation. Consider, for a compelling example, Antarctica. Today it stands as the icy crown of the southern hemisphere, buried beneath kilometers of snow and home to some of the most bone-chilling temperatures on Earth. But it wasn't always this way. Approximately 35 million years ago, Antarctica began its slow, deliberate separation from South America and Australia. This monumental geological event, known as the opening of the Drake Passage between South America and the Antarctic Peninsula and the Tasmanian Gateway between Australia and East Antarctica, allowed the vast, unobstructed expanse of the Southern Ocean to form. This crucial opening allowed the Antarctic Circumpolar Current, ACC, to form, a powerful, relentless band of cold water that perpetually circles the continent from west to east, effectively insulating it from warmer ocean currents and creating a potent thermal barrier. As this current gained strength and became fully established, it dramatically isolated Antarctica from global heat exchange, causing its climate to cool dramatically, and colossal glaciers began their relentless formation, ultimately leading to the massive ice sheet we see today. This transition marked the beginning of the Cenozoic era's overall cooling trend and the formation of the Antarctic ice sheet, a key step in the current Quaternary Ice Age. Or let us ponder the awe-inspiring Himalayas. These towering peaks were born when the Indian subcontinent, a colossal landmass that had drifted northward for millions of years after breaking from the supercontinent Gondwana, majestically slammed into Asia approximately 50 million years ago. First, a monumental continental collision that continues to this very day, pushing the mountains higher, millimeter by millimeter, a testament to the immense forces at play. The prodigious rise of the Himalayas and the vast Tibetan Plateau had a profound and enduring effect on global weather patterns and the long-term carbon cycle. Their sheer unparalleled size disrupts atmospheric air currents, fundamentally alters monsoon systems across Asia, and significantly increases rock weathering, a crucial geological process that draws vast quantities of carbon dioxide out of the atmosphere. When exposed to rain and atmospheric gases, particularly carbonic acid, H2CO3, formed when CO2 dissolves in rainwater, rocks undergo chemical reactions, e.g., the silicate weathering of minerals like feldspar and calcium silicates, that consume atmospheric CO2, forming soluble bicarbonate ions and insoluble carbonate minerals, which are then transported by rivers to the oceans and sequestered in sedimentary rocks on the seafloor. This removal of CO2, a potent greenhouse gas from the atmosphere in turn, leads to a noticeable cooling of the planet over millions of years, contributing to the overall cooling trend of the Cenozoic era. It's as if the continents themselves are colossal thermostats, maneuver them into the correct positions, create the right mountain ranges, and you can cool the planet sufficiently for immense glaciers to grow. And once ice begins to accumulate, a fascinating phenomenon occurs. It tends to encourage even more of its frosty brethren. This self-perpetuating cycle is attributed to something called albedo, a measure of how much sunlight a surface reflects back into space. The Earth's average albedo is about 0.3, meaning it reflects 30% of incoming sunlight. However, Ice and snow are exceptionally reflective surfaces, with an albedo of 0.8–0.9, meaning they reflect 80 to 90% of incoming sunlight, efficiently bouncing incoming sunlight back into the cosmos and thereby preventing that vital energy from warming the planet's surface. Consequently, the more ice present, the more sunlight is reflected and the colder the planet becomes. And the colder it gets, the more ice forms, creating a powerful positive feedback loop that can, under the right conditions, spiral into some truly frigid and planet-altering consequences. This ice albedo feedback is a critical amplifier of initial cooling. Other feedback mechanisms also play a part. For example, as the Earth cools, the capacity of the oceans to dissolve CO2 increases, drawing more greenhouse gas out of the atmosphere and further accelerating cooling, a negative feedback to warming but a positive feedback to cooling. Conversely, as oceans warm, they release dissolved CO2, exacerbating warming. Changes in vegetation cover also contribute. As climates cool, vast forests recede, replaced by tundra and grasslands, which often have higher albedo, especially seasonally, when covered by snow, contributing to further cooling. Changes in cloud cover and atmospheric water vapor, itself a potent greenhouse gas, also provide complex feedback loops that can either amplify or dampen temperature changes, adding to the climate system's complexity. But ice ages are not solely about frozen landscapes and intricate geological mechanics. They have exerted a profound, undeniable, and often brutal effect on life itself. Glaciations have repeatedly and dramatically reshaped Earth's ecosystems, compelling species to adapt with remarkable speed, migrate to new, more hospitable territories, or tragically perish in the face of overwhelming cold. These periods of extreme environmental stress act as powerful filters, driving evolutionary change and diversification among surviving populations, leading to the rise of new adaptive traits and the extinction of less resilient forms. The ebb and flow of ice sheets created distinct geographical barriers, leading to allopatric speciation, the formation of new species due to geographical isolation, as populations became separated by ice and evolved independently. Entire landscapes have been meticulously sculpted by the relentless grinding power of glaciers, carving out majestic U-shaped valleys with their immense weight, slowly grinding down towering mountains, creating spectacular fjords, e.g. in Norway, Greenland and coastal British Columbia, and leaving behind the unmistakable fingerprints of ice across every continent, from Scandinavia to Patagonia. These distinctive geological signatures provide invaluable records for paleoclimatologists to reconstruct past ice extent, ice dynamics, and climate conditions, helping us piece together Earth's climatic history. In many profound ways, ice ages serve as nature's grand refresh button. They meticulously clear the slate, reshuffle the deck of life, and ultimately set the stage for explosive evolutionary bursts and the emergence of entirely new, complex ecosystems. Without the cyclical, frigid embrace of ice ages, humans might never have ventured forth from Africa and populated the globe. Woolly mammoths might have remained a fleeting figment of imagination, and your cozy valley town might still lie entombed beneath kilometers of ancient ice. So the next time winter seems to overstay its welcome, and you find yourself grumbling at the treacherous icy sidewalk, take heart. It's all part of a much, much grander narrative. A story that stretches back millions of years and intricately weaves together geology, astronomy, biology, and the very evolution of life on Earth. And that, dear listener, is precisely what makes ice ages so utterly compelling. They are not merely frozen footnotes in history. They are the slow, patient, and powerful rhythms of a living planet. Cold undoubtedly, harsh at times, but also undeniably deeply beautiful. They serve as a poignant reminder that Earth is never truly static. It breathes, it shifts, it freezes, and it thaws, all in perfect synchronicity with forces far vaster and more ancient than any mere daily weather report. So tonight, as you sink deeper into the comforting embrace of your pillow, allow your thoughts to drift not just to desolate frozen tundras and majestic icy mountains, but to the quiet, immense power of deep time and the comforting realization That through all its profound ages and dramatic upheavals, Earth keeps turning, ice and all, the ice ball that almost was, unraveling the Snowball Earth. Hypothesis: an immersive exploration of extreme climate and its aftermath imagine. Earth not. As the vibrant, bustling planet we know today, teeming with sprawling cities, verdant forests and cerulean oceans, but as a colossal frozen sphere locked in an impenetrable shroud of ice from pole to equator, a pristine white marble silently drifting through the cosmic expanse, reflecting almost all incoming sunlight back into the void. There are no gentle waves caressing tropical shores, no emerald leaves fluttering softly in the breeze, just an unending expanse of glaciers stretching limitlessly across continents, and a sea encased in a formidable shell of ice, thick enough to completely engulf entire mountain ranges. This, my curious dreamer, is the chilling yet utterly captivating world of Snowball Earth. It represents one of the most extreme and truly catastrophic climate events our planet has ever endured, dwarfing any ice age in the last few million years. It sounds like a fantastical premise plucked straight from the pages of science fiction, but it is, in fact, one of the most intriguing and rigorously supported ideas in modern geology and paleoclimatology. And the most astonishing part: it likely happened not once but on multiple occasions throughout Earth's history, millions of years apart, during a geological period known as the Cryogenian, from roughly 720 to 635 million years ago, a time preceding the rise of complex animal life. Let's meticulously set the stage for this incredible journey into deep time. We are traveling back, way back, hundreds of millions of years before the majestic reign of dinosaurs, before the very emergence of the first ferns and complex land plants, and long before the earliest complex animals tentatively ventured to crawl across the seafloor. The planet, in many crucial respects, was still in its formative years, with life just beginning its tentative experiments with the concept of multicellularity and complexity. Most living organisms were single-celled, silently drifting and flourishing in ancient oceans that covered a substantial portion of the globe. There were no towering trees, no shimmering fish, and unequivocally no humans. Just a primordial soup of resilient bacteria, primitive algae, and other microscopic pioneers inhabiting a world far different from our own. A world defined by its primordial simplicity and the burgeoning development of photosynthesis. Then, sometime around 720 million years ago, something profoundly changed. The climate began its inexorable descent into cooling, slowly at first, then with accelerating drama and intensity. Ice commenced its relentless formation at the poles, subsequently creeping outward, a frigid, unstoppable tide engulfing the vast landmasses of the continents. The cooling intensified dramatically, and soon colossal glaciers were inexorably rolling over the land, carving out majestic valleys with their immense weight and piling up like gargantuan bulldozers crafted from frozen time. The oceans too began to succumb to the biting chill, freezing not just at the surface, but quite possibly extending hundreds of meters deep beneath the waves, turning oceans into vast, solid ice sheets that would have stifled almost all marine life, plunging much of the biosphere into a long, dark winter, cutting off light for photosynthesis. This deep, oceanic freezing would have severely restricted the exchange of gases between the atmosphere and the oceans, impacting various biogeochemical cycles like the carbon and oxygen cycles, and suffocating marine life by cutting off sunlight for photosynthesis. And then, an eerie, profound silence descended upon the planet. Earth was sealed in an icy, silent tomb, a ghostly white orb, its very existence defined by the absence of warmth and fluidity, a stark contrast to its vibrant past and future. The compelling evidence for this astonishing hypothesis isn't merely theoretical. It's robustly etched within the very rocks themselves. Yes, rocks in their silent majesty can recount extraordinary tales, especially those formations meticulously shaped by ancient glacial forces. All over the world, geologists have unearthed distinct layers of rock that bear an uncanny resemblance to those formed beneath immense ancient glaciers. These are scientifically known as tillites, chaotic jumbles of broken stone and debris, unsorted and angular, reflecting their deposition by ice, not water, meticulously deposited as massive. Ice flows melt and recede, leaving behind a unique geological fingerprint. What makes these discoveries particularly baffling and significant is that we find these unmistakable glacial deposits not merely in the vicinity of the poles, where their presence would be perfectly anticipated, but astonishingly in what would have been ancient tropical zones at that distant time, places like Namibia, Australia, and the Congo. How could this possibly be? The only logical explanation for the pervasive existence of tropical glaciers is if the entire planet was engulfed in an unprecedented, truly profound, and ubiquitous cold, extending even to the equator. Another crucial clue emerges from the observation of dropstones. These are large, anomalous chunks of rock that appear conspicuously out of place, embedded within fine-grained marine sediments far from any obvious land source or river delta. These rocks likely hitched a ride on ancient icebergs, which, having floated out over the vast expanse of the ocean, eventually melted, ceremoniously dropping their rocky cargo into the soft, yielding seafloor mud. When scientists meticulously date these rocks and meticulously analyze their magnetic orientation, a technique called paleomagnetism, which records the Earth's magnetic field at the time the rock formed, allowing reconstruction of its ancient latitude, they reveal a startling and consistent truth. These dropstones were deposited near the ancient equator. In other words, there were icebergs in the tropics. This wasn't merely a fleeting cold snap. This was a planetary deep freeze, a global refrigeration of unprecedented scale. Further geochemical evidence, such as anomalous carbon isotope ratios, specifically extremely light values of carbon-13, denoted as D13C, in ancient marine sediments, also supports the idea of drastically altered carbon cycling, consistent with widespread ice cover, and dramatically reduced biological activity in the oceans, as photosynthesis would have been severely limited, leading to a biological crash. Some layers also show banded iron formations, BIFs, thick layers of alternating iron-rich and silica-rich rock, usually associated with anoxic, oxygen-poor ocean conditions, which suggests limited interaction between the atmosphere and deep ocean, consistent with a thick ice cover preventing atmospheric oxygen from reaching the deep ocean, allowing dissolved iron to accumulate and then precipitate out when oxygen was reintroduced. So how did such an extreme and all-encompassing event unfold? Scientists posit that it may have been initiated by a complex sequence of unfortunate geological and astronomical coincidences. Firstly, the supercontinent Rodinia was in the process of fracturing and breaking apart, particularly along the equator. This colossal geological event exposed vast stretches of fresh, unweathered silicate rock to the atmosphere, especially in the tropical regions. Such rock has an inherent tendency to absorb carbon dioxide, a crucial and powerful greenhouse gas, through a process called chemical weathering. When rainwater, slightly acidic from dissolved CO2, forming carbonic acid H2CO3, reacts with silicate minerals, e.g. calcium silicates, it consumes atmospheric CO2, forming soluble bicarbonate ions and insoluble carbonate minerals, which are then transported by rivers to the oceans and sequestered in sedimentary rocks on the seafloor. With increased continental landmasses in the tropics, where weathering is most efficient due to higher rainfall and temperatures, and thus continuously reduced atmospheric carbon dioxide, the planet inexorably began its slow, steady descent into cooling. Secondly, Earth was receiving slightly less energy from the sun than it does in the present day. The sun back then was younger and a tad dimmer, its output not as robust as today's. This is known as the faint young sun paradox, explaining how Earth remained warm enough for liquid water early in its history, despite a fainter sun. Add in a few well-timed volcanic eruptions, which paradoxically can inject reflective particles like sulfur aerosols into the upper atmosphere, thereby increasing Earth's albedo and further cooling the planet, and the stage was perfectly set for a sudden dramatic slip into a world of profound snow and chilling silence. Once glaciers began their relentless and unstoppable expansion, they may have triggered a catastrophic self-perpetuating feedback loop known as ice albedo feedback. Here's how this chilling yet elegant mechanism operates. Ice and snow are exceptionally reflective surfaces with an albedo of up to 0.9, meaning they reflect 90% of incoming sunlight. They efficiently bounce incoming sunlight back into space, thereby preventing that vital energy from warming the planet's surface. Consequently, the more ice present, the more sunlight is reflected and the colder the planet becomes. And the colder it gets, the more ice forms, creating a powerful positive feedback loop that could theoretically push the planet into a complete freeze. It's a runaway process, one that, given the precise conditions, could indeed lead to a nearly completely frozen planet, a white marble orbiting the sun, a self-sustaining refrigeration system that would be incredibly difficult to overcome due to the immense reflectivity of a globally ice-covered surface. But was Earth truly frozen solid, a solid sphere of ice? This is where a fascinating and ongoing scientific debate unfolds. Some researchers contend that the term Snowball Earth might be a touch too dramatic, perhaps an oversimplification of the geological evidence, even if it captures the general severity. Instead, they propose a slush-ball Earth scenario, a planet still largely frozen, but with tantalizing thin patches of open water persisting near the equator, perhaps due to persistent volcanic activity, specific oceanic circulation, patterns or thin ice in certain regions, allowing some solar penetration. These delicate blue ribbons of unfrozen water, though scarce, may have been just enough to sustain life, albeit barely, providing refugia for marine organisms. After all, even during the most bone-chilling periods, resilient bacteria and primitive algae likely managed to survive in isolated pockets of liquid water, perhaps in geothermal springs located beneath the colossal sea ice or near active undersea volcanic vents, hydrothermal vents, where heat from Earth's interior could escape, creating vital oases of warmth and nutrients, much like the thriving chemosynthetic ecosystems found around deep-sea vents today. These refugia are key to explaining how life bounced back with such vigor and diversity, as they would have preserved the genetic diversity necessary for rapid post-glacial evolution. This leads us to a question that is both profoundly fascinating and eerily resonant. If the entire planet was indeed encased in an impenetrable layer of ice, how did life not only survive, but subsequently thrive with such astonishing vigor and diversity? One compelling hypothesis suggests that these extreme conditions may have acted as an intense evolutionary pressure cooker. Life was pushed to its absolute limits, compelled by the sheer force of survival to adapt, evolve, and innovate with unprecedented urgency. The severe environmental stress could have wiped out less resilient forms, leaving only the most adaptable to pass on their genes. The surviving populations, confined to harsh, isolated refugia, would have experienced intense, selective pressures, potentially accelerating the rate of evolutionary change through strong natural selection. After each snowball episode, when the ice finally relinquished its crushing grip, Earth experienced an explosion of biological creativity, a veritable Cambrian explosion in miniature. Some scientists even propose that these deep freezes were instrumental in paving the way for the emergence of multicellular life, and ultimately, the astonishing diversity of animals we see today, including ourselves. The genetic bottlenecks and extreme selective pressures could have driven rapid evolutionary change and facilitated the development of new metabolic pathways, adaptations for coping with extreme environments, such as cold resistance or dormancy, and the evolution of sexual reproduction, which dramatically increased genetic variation, providing more raw material for natural selection to act upon, speeding up the evolutionary process. Escaping the ice prison, the volcano's fiery rescue, and the post-glacial rebirth. A detailed account of planetary recovery and biological flourishing, but what about the thaw? How did Earth manage to escape its seemingly inescapable icy prison, to break free from its frozen tomb? The answer once again resides in the surprising, slow and powerful accumulation of carbon dioxide, CO2, but this time primarily from deep within the Earth, expelled by its internal geological processes. During the Snowball Earth period, with the vast majority of the planet covered in ice, the natural weathering processes that typically remove carbon dioxide from the atmosphere would have drastically slowed down or even ceased entirely. The land was covered by kilometers of ice, preventing direct contact with the atmosphere. Rivers weren't flowing over exposed rock, and the rocks weren't exposed to rain and atmospheric CO2, thus effectively stopping the geological scrubbing of CO2 from the air. However, volcanoes, those tireless geological engines driven by plate tectonics, kept erupting with unwavering consistency, whether at mid-ocean ridges, subduction zones, or hotspots, continuously belching out prodigious quantities of greenhouse gases like CO2, methane, and water vapor into the atmosphere, completely oblivious to the frozen surface world. With nowhere for the accumulating carbon dioxide to be sequestered and removed through weathering, it steadily built up in the atmosphere over millions of years, transforming the planet's atmosphere into a slow-motion pressure cooker of warming, reaching atmospheric concentrations potentially hundreds to thousands of times higher than today's levels. Eventually, the concentration of atmospheric carbon dioxide reached a critical threshold, powerful enough to overpower the relentless icy albedo feedback loop. The planet began to warm, and when it started, it didn't merely warm gently. Oh no, it swung dramatically and rapidly in the opposite direction, with almost theatrical flair, in what is sometimes called a super greenhouse event. This sudden intense warming would have led to rapid ice melt, as the increased CO2 trapped enough heat to overcome the reflectivity of the ice. The melting probably started near the equator, where solar insolation was highest, and then propagated rapidly poleward as more dark ocean and land were exposed, further absorbing sunlight and accelerating the thaw in a runaway positive feedback. This rapid deglaciation would have been geologically instantaneous, perhaps occurring over mere thousands of years, a blink in geological time, especially compared to the millions of years of freezing. The evidence for this rapid thaw often includes unique geological features like cap carbonates, thick layers of carbonate rock that directly overlie tillites, indicating a rapid precipitation event likely caused by the sudden chemical changes in the oceans due to massive meltwater input and extreme CO2 concentrations reacting with the water. When the monumental ice sheets finally began their retreat, they did so with astonishing rapidity, unleashing a cascade of profound environmental changes. Glaciers melted at an unprecedented rate, oceans thawed, and colossal floods likely swept across the continents, carving out new landscapes and transporting immense loads of sediment into the warming seas. This rapid melting would have dramatically altered sea levels and coastal geomorphology, leading to widespread erosion and deposition of unique sedimentary sequences. The sheer volume of meltwater would have created vast proglacial lakes formed at the front of a glacier, dammed by ice or moraines, and mega floods, evidence of which can be found in places like the channeled scablands of eastern Washington state in North America, formed by the sudden draining of glacial Lake Missoula, which released torrents of water and ice across the landscape. With the melting, an influx of nutrient-rich runoff derived from the grinding of fresh rocks by glaciers and the accumulated volcanic ash poured into the oceans, fertilized by the freshly weathered rocks exposed by the receding ice. This sudden burst of nutrients, including iron, phosphorus, nitrogen, and other trace elements, may have played a pivotal role in waking up the biosphere, providing the essential building blocks for life. Algae and cyanobacteria, long confined to eking out a precarious existence in narrow pockets of liquid water beneath the ice, now found themselves immersed in a world of boundless opportunity. Sunlight permeated the oceans, nutrients swirled through the burgeoning currents, and life responded with an unparalleled flourish of growth and diversification, creating vast algal blooms that absorbed massive amounts of CO2 from the atmosphere, a biological pump, further influencing the carbon cycle and providing a biological pump to sequester carbon on the seafloor as organic matter. Some researchers even believe that these post-glacial blooms helped to lay the groundwork for the rise of complex multicellular organisms, leading directly to the Cambrian explosion of diverse animal life forms, approximately 541 million years ago, marking a dramatic increase in biological complexity, ecological interactions, and the emergence of hard parts, skeletons, shells, in the fossil record. In other words, the very ice that nearly extinguished life may have, in a remarkable twist of fate, provided the crucial spark that helped it flourish, demonstrating a profound link between extreme environmental stress and evolutionary innovation. It's worth noting that Earth didn't merely thaw once from a global freeze. There were likely two major Snowball Earth events during the Cryogenian period, from about 720 to 635 million years ago. First, the Sturtian glaciation around 720 million years ago, and then the Marinoan glaciation around 630 million years ago. Some evidence even suggests a third, less severe event, the Glaciers glaciation, around 580 million years ago, though its global extent is still debated. Each of these extraordinary events may have endured for tens of millions of years, representing truly unimaginable durations of extreme cold. That's an unfathomable amount of time to be frozen solid, and an equally immense amount of time for volcanic gases to relentlessly accumulate in the atmosphere, pushing the planet towards its dramatic thaw. Following the Marinoan episode, Earth transitioned into a much warmer and significantly more stable period known as the Ediacaran period, 635 to 541 million years ago. This is when we begin to observe the earliest tantalizing traces of large, soft-bodied organisms in the fossil record, distinct from the microbial life that dominated before. They were peculiar, almost alien-looking creatures, frond-like forms delicately pressed into ancient seafloors, or discoidal shapes representing some of the earliest macroscopic life, often thought to be early animals or their close relatives, but their exact phylogenetic relationships are still a subject of intense research. But what is unequivocally clear is that life had undergone a monumental leap forward in complexity and size, paving the way for the later Cambrian explosion. The idea that cataclysmic ice could ultimately lead to profound evolutionary progress is both deeply fascinating and possesses a certain poetic elegance. It suggests that life doesn't merely endure hardship, it fundamentally transforms through it, becoming stronger and more complex. Pressure, as the adage goes, makes diamonds. And in the extraordinary case of Snowball Earth, profound cold forged, unprecedented complexity and diversification of life, demonstrating the incredible resilience and adaptive capacity of biological systems to even the most extreme planetary conditions. But returning to the physical planet itself, the transition from a truly global snowball state to a significantly warmer climate wasn't solely a biological revolution. It was a simultaneous geological and atmospheric upheaval as well. As the ice melted, the newly exposed land began to undergo chemical weathering once again, steadily drawing carbon dioxide back out of the atmosphere. Over protracted periods, this process would contribute to stabilizing the climate, gradually drawing down the intense greenhouse gases and eventually restoring a delicate balance, returning Earth to a more moderate greenhouse state. The vital water cycle resumed its ancient rhythm. Rivers flowed freely once more, carving new paths across the landscape. Majestic storms rolled across the newly reawakened skies, bringing precipitation and driving the global hydrological cycle. Earth had, in essence, reawakened from its icy slumber, reborn into a new era of warmth and vibrant life, having undergone a complete planetary reset. Interestingly, this dramatic swing from frozen silence to roaring warmth is one of the primary reasons why the Snowball Earth hypothesis is still a subject of ongoing scientific debate and refinement. Some researchers suggest that a full global freeze was unlikely, and instead propose a slushball Earth scenario, where some equatorial oceans remained unfrozen, allowing for greater continuity for marine life, and perhaps moderating the subsequent rebound warming. It's a subtle but crucial distinction, as it alters our understanding of Earth's climate sensitivity and the remarkable resilience of early ecosystems in extreme conditions. Nonetheless, the evidence for at least near-global glaciations during the Cryogenian is robust and widely accepted by the scientific community. The Snowball Earth hypothesis continues to be an active area of research, with ongoing efforts to refine the timing, extent, and mechanisms of these ancient planet-altering events, utilizing new geochemical proxies like sulfur isotopes, which can indicate atmospheric oxygen levels or the presence of specific metabolic pathways, and sophisticated climate modeling. Still, Even the most conservative scientific models concur that something profoundly significant, an event of immense scale, occurred during the cryogenian period. Whether it was a total snowball or a patchy slush ball, the planet undeniably endured one of the most extreme climate swings in its entire history. And life, against all odds, not only survived, but triumphantly set the stage for all future complexity and diversity. The irony, of course, is exquisitely delicious. The very phenomenon that nearly extinguished life may have, in a remarkable twist of fate, provided the crucial spark that helped it flourish. Earth, in its seemingly self-destructive pursuit of cold, may have inadvertently given life the evolutionary nudge it so desperately needed. And it achieved this not through mere chaos, but through intricate cycles, sophisticated chemistry, and the slow, relentless grind of geology and planetary evolution. Continental drifters, the role of plate tectonics in Earth's climate. An intricate dance of land, sea, and atmospheric chemistry. Imagine Earth's continents not as immutable, fixed pieces of geography, but as colossal, slow-moving rafts, gently drifting atop a vast, churning sea of semi-molten rock within the planet's mantle. This is the asthenosphere, a ductile layer beneath the rigid lithosphere, Earth's crust and uppermost mantle, that allows the tectonic plates to move. These plates are driven by mantle convection, where heat from the Earth's core and mantle drives slow convective currents, pushing and pulling the overlying plates. Over unimaginable spans of millions of years, they wander across the globe, majestically collide, giving rise to towering mountain ranges, and then, with equal grandeur, break apart again, forming new ocean basins, all in a planetary game of bumper cars played out in exquisitely slow motion. This, my curious dreamer, is plate tectonics, the subtle yet relentless movement of Earth's lithosphere, its outermost rigid shell, fragmented into giant plates. And it plays a starring, often overlooked but absolutely fundamental role in the grand climatic saga that includes our planet's magnificent ice ages. At first glance, it might not be immediately apparent how the mere placement of continents could exert such a profound influence on something as vast and dynamic as the global climate. After all, how can the glacial crawl of land masses, moving at rates of only a few centimeters per year, roughly the speed your fingernails grow, possibly influence global temperatures, let alone tip the entire planet into a deep, sustained freeze? But the profound truth is that the precise geographical location and configuration of continents has an incredibly powerful effect on how heat and moisture are distributed and moved around the planet, and ultimately, where towering ice sheets thrive or conversely wither away. Let's begin with something seemingly simple, yet incredibly powerful: ocean currents. These vast, powerful rivers of moving water, both surface currents, driven by wind, solar heating, and Coriolis effect, and deep ocean currents, driven by differences in temperature and salinity, known as thermohaline circulation, or the global conveyor belt, are in essence the intricate arteries of the global climate system. They diligently carry heat from the equator towards the poles and play a crucial role in balancing temperature differences across the entire globe, moderating climates worldwide and influencing regional precipitation. However, they do not simply flow wherever they please. They are meticulously shaped and steered by the arrangement of the continents and the seafloor topography. When continents migrate, they fundamentally alter the shape and depth of the ocean basins, which in turn precisely reshapes the direction, speed, and intensity of these vital currents. A seemingly minor shift in continental position can redirect warm water away from the poles, preventing it from reaching and melting existing ice, or conversely, trap frigid water in deep basins, both of which can unleash dramatic and far-reaching impacts on the global climate. For instance, the formation of land bridges like the Isthmus of Panama, which closed around 3 to 4 million years ago and created a complete barrier between the Pacific and Atlantic Oceans. This event significantly altered Atlantic Ocean circulation, intensifying the Gulf Stream, a warm ocean current flowing from the Gulf of Mexico towards Europe and the Arctic, and perhaps increasing moisture transport to higher latitudes in North America and Eurasia, providing the necessary snowfall for glaciation in the Northern Hemisphere, thus potentially contributing to the onset of the Quaternary Ice Age by delivering moisture to high latitudes where it could fall as snow and accumulate. Conversely, the opening of new seaways like the Drake Passage between South America and Antarctica, around 35 million years ago, can allow cold water to circulate freely around polar land masses, enhancing their thermal isolation and promoting glaciation. Consider, for a compelling example, Antarctica. Today it stands as the icy crown of the southern hemisphere, buried beneath kilometers of snow and home to some of the most bone-chilling temperatures on Earth. But it wasn't always this way. Approximately 35 million years ago, Antarctica began its slow, deliberate separation from South America and Australia. This monumental geological event, known as the opening of the Drake Passage, between South America and the Antarctic Peninsula and the Tasmanian Gateway, between Australia and East Antarctica, allowed the vast, unobstructed expanse of the Southern Ocean to form. This crucial opening allowed the Antarctic Circumpolar Current, ACC, to form, a powerful, relentless band of cold water that perpetually circles the continent from west to east, effectively insulating it from warmer ocean currents and creating a potent thermal barrier. As this current gained strength and became fully established, it dramatically isolated Antarctica from global heat exchange, causing its climate to cool dramatically, and colossal glaciers began their relentless formation, ultimately leading to the massive ice sheet we see today. This transition marked the beginning of the Cenozoic era's overall cooling trend and the formation of the Antarctic ice sheet, a key step in the current Quaternary Ice Age. Or let us ponder the awe-inspiring Himalayas. These towering peaks were born when the Indian subcontinent, a colossal landmass that had drifted northward for millions of years after breaking from the supercontinent Gondwana, majestically slammed into Asia approximately 50 million years ago. A monumental continental collision that continues to this very day, pushing the mountains higher, millimeter by millimeter, a testament to the immense forces at play. The prodigious rise of the Himalayas and the vast Tibetan Plateau had a profound and enduring effect on global weather patterns and the long-term carbon cycle. Their sheer unparalleled size disrupts atmospheric air currents, fundamentally alters monsoon systems across Asia, and significantly increases rock weathering, a crucial geological process that draws vast quantities of carbon dioxide out of the atmosphere. When exposed to rain and atmospheric gases, particularly carbonic acid, H2CO3, formed when CO2 dissolves in rainwater, rocks undergo chemical reactions, e.g., the silicate weathering of minerals like feldspar and calcium silicates, that consume atmospheric CO2, forming soluble bicarbonate ions and insoluble carbonate minerals, which are then transported by rivers to the oceans and sequestered in sedimentary rocks on the seafloor. This removal of CO2, a potent greenhouse gas from the atmosphere in turn, leads to a noticeable cooling of the planet over millions of years, contributing to the overall cooling trend of the Cenozoic era. It's as if the continents themselves are colossal thermostats. Maneuver them into the correct positions, create the right mountain ranges, and you can cool the planet sufficiently for immense glaciers to grow. But plate tectonics doesn't solely influence ice formation through mere geography. It also profoundly affects the very chemistry of the planet's atmosphere, particularly the carbon cycle, which is the primary long-term regulator of Earth's climate. When towering mountain ranges majestically rise due to continental collisions, they expose vast quantities of fresh rock to the surface. This fresh rock then undergoes chemical weathering when exposed to rain, wind, and atmospheric gases. This process efficiently pulls carbon dioxide from the air and locks it into minerals, thereby contributing to the cooling of the climate over millions of years. This geological carbon pump is a critical long-term climate regulator. When continents collide, they can also trap significant amounts of organic carbon, derived from ancient life forms that have accumulated in sediments within the Earth's crust as sedimentary rocks, effectively removing it from the active carbon cycle for millions of years, further contributing to atmospheric CO2 drawdown. Conversely, when volcanoes erupt, often at the dynamic plate boundaries, like mid-ocean ridges where new crust is formed, subduction zones where one plate slides beneath another, and hotspots where plumes of magma rise from the deep mantle, They can inject colossal amounts of carbon dioxide and other gases, like sulfur dioxide, which can lead to cooling aerosols, back into the atmosphere, warming things up again. This release of CO2 by volcanism is the primary long-term source of atmospheric carbon, which balances the removal by weathering, maintaining the overall carbon budget over geological timescales. It is, in essence, a long, slow, and intricate conversation between the Earth's churning crust and its ever-changing climate, a perpetual push and pull, a gradual and complex negotiation that spans eons, determining the planet's baseline temperature over geological timescales. One of the most fascinating aspects of this intricate interplay between plate tectonics and climate is just how indirect its effects can be, often involving complex feedback loops that amplify or dampen initial changes. A seemingly minor shift in one continent's position might trigger cascading changes in ocean circulation, which in turn affects global rainfall patterns, which subsequently influences plant growth and thus carbon uptake, which ultimately alters atmospheric carbon levels, which finally affects global temperatures. It's a vast, intricate chain of dominoes, and it can take millions of years for the entire sequence to fall, demonstrating the profound interconnectedness and systemic nature of Earth's various subsystems, from the solid Earth to the atmosphere and oceans. So, while it may seem peculiar to attribute the triggering of an ice age to the majestic rise of mountains, or to blame the fragmentation of a supercontinent for a frozen equator, that is precisely the kind of profound cause and effect we observe. Throughout Earth's deep geological history, all of this serves as a powerful reminder that our planet is anything but static. It is alive, in a slow, majestic, and awe-inspiring sort of way. The continents gracefully shift, the oceans rearrange their vast currents, and the climate responds in kind. Ice ages come and go, not merely because of distant stars or invisible gases, but because the very ground beneath our feet is always on the move. And though these monumental movements are far too slow for us to perceive within a single human lifetime, over the immense sweep of geological time, they meticulously shape the world in ways that are both profound and exquisitely beautiful. A snow-covered mountain range, a deep enigmatic ocean trench, a fertile valley meticulously carved by ancient glaciers, each of these tells a compelling story of Earth's restless crust and its quiet, yet immensely powerful, influence on the climate we inhabit. Earth's cosmic dance, the Milankovitch cycles as climate pacemakers, an astronomical perspective on orbital influences and their amplification. If you've ever observed Earth's orbit illustrated in a typical science textbook, you might have noticed that it's often depicted as a neat, almost perfect ellipse, a slightly squashed circle with the sun positioned slightly off to one side. That simplified image, while helpful for initial understanding, doesn't quite capture the full breathtaking elegance and dynamism of our planet's cosmic choreography. Because Earth's orbit isn't merely fixed and predictable, it's in a state of perpetual graceful motion, subtly influenced by the gravitational tug of other planets in our solar system, particularly the massive gas giants Jupiter and Saturn, which exert a cumulative pull over vast timescales. It wobbles, it shifts, it tilts, and it stretches, and these seemingly minute, almost imperceptible changes, when accumulated over tens of thousands of years, possess the astonishing power to determine whether colossal glaciers expand their frosty dominion, or conversely, melt away into the vast oceans. Welcome, curious dreamer, to the mesmerizing world of the Milankovitch cycles, named after the brilliant Serbian mathematician and astronomer Milutin Milankovic, who painstakingly calculated their influence on Earth's climate in the early 20th century, providing the theoretical framework that was later confirmed by meticulous geological and paleoclimatic evidence from ocean sediments and ice cores. These cycles are a set of 3 long-term cyclical variations in Earth's orbital and axial movements that profoundly influence how sunlight, the very engine of our climate, is distributed across the planet's surface. Think of them as slow, celestial nudges that precisely adjust the Earth's climate over vast spans of time, not in dramatic day-to-day ways, but in grand, rhythmic planetary pulses that set the beat for glacial and interglacial periods within a larger ice age. Let's embark on our exploration with the first of these captivating cycles, eccentricity. This term refers to the precise shape of Earth's elliptical orbit around the Sun. When the orbit is a perfect circle, eccentricity is 0. Currently, Earth's orbit is remarkably close to being circular, with a relatively low eccentricity of about 0.0167, fluctuating between nearly 0, a perfect circle, and about 0.06, a more elongated ellipse, meaning that we maintain almost the same distance from the Sun throughout the entire year. This results in relatively consistent solar insolation, incoming solar radiation, throughout our annual journey. However, this perfectly circular state isn't a constant. Over a monumental cycle of approximately 100,000 years, with a secondary, longer cycle of about 400,000 years, driven by the gravitational pull of Jupiter and Saturn, the orbit undergoes a transformation, becoming more elliptical, more elongated or squashed, then gradually less elliptical, and then returning to its more circular form. When the orbit is more stretched out, higher eccentricity, the difference in solar energy received between Earth's closest point to the Sun, perihelion, and its farthest point from the Sun, aphelion, becomes far more pronounced, while the total annual insolation received by the Earth changes only minimally, about 0.1–0.2%. This subtle yet significant variation amplifies seasonal differences in solar radiation. When the orbit is more elliptical, and one hemisphere's summer occurs at perihelion, Earth closest to the Sun, that summer will be significantly warmer. Conversely, if summer occurs at aphelion, Earth farthest from the Sun, it will be cooler. This enhanced seasonality can have profound effects on the onset or termination of glacial periods, particularly by influencing the intensity of summer at high latitudes. Next, we delve into obliquity, often referred to as axial tilt. This is the precise angle between Earth's rotational axis and its orbital plane around the Sun, the ecliptic plane. Currently, Earth is tilted at approximately 23.5 degrees relative to its orbit. This tilt is what gives us our seasons, as different parts of the Earth are tilted towards or away from the Sun at different times of the year, leading to variations in solar intensity and day length across the globe. Without a tilt, there would be no seasons, and the climate would be much more uniform across latitudes. However, over a cycle lasting roughly 41,000 years, that tilt can subtly increase to nearly 24.5 degrees, leading to more extreme tilts, or decrease to just over 22.1 degrees, leading to less pronounced tilts. The degree of Earth's tilt directly dictates the severity of the seasons. A greater tilt translates to more extreme seasons, hotter summers, and significantly colder winters, as the poles receive more direct sunlight in summer and less in winter. Conversely, a smaller tilt leads to noticeably milder seasons, reducing the contrast between summer and winter and ensuring less extreme solar radiation at the poles. These subtle changes in tilt can critically affect how much summer melting occurs at high latitudes, which is an absolutely pivotal factor in determining whether vast ice sheets advance or, conversely, majestically retreat. If summers are too warm, even abundant winter snow will melt, preventing glacier growth regardless of how much snow fell in winter. It's the cumulative effect of unmelted snow year after year that gradually builds up and compresses into dense glacial ice. A smaller tilt means less summer insolation at high latitudes, which favors ice sheet growth by reducing summer melt. The third and final cycle is precession, which is a rather elegant way of describing the fact that Earth wobbles, like a gracefully spinning top on its axis. This wobble is caused by the gravitational pull of the Sun and Moon on Earth's equatorial bulge, the slight bulging at the equator due to Earth's rotation. Over a cycle of about 23,000 years, comprising two main components with periods of roughly 19,000 and 23,000 years, due to the slightly different rates of lunar and solar precession, the direction of Earth's axis slowly, imperceptibly rotates, completing a full circle in space relative to the fixed stars. This subtle wobble fundamentally changes the timing of the seasons relative to Earth's precise position in its orbit. For example, Currently, the Northern Hemisphere's summer occurs when Earth is at its farthest point from the Sun, aphelion, occurring around early July, which slightly moderates Northern Hemisphere summers. But in approximately 11,000 years, this will reverse. Summer in the Northern Hemisphere will occur when Earth is at its closest point to the Sun, perihelion, occurring around early January, thereby making those summers notably warmer, assuming all other factors remain constant. Conversely, this also affects the severity of winter. The combined effect of precession and eccentricity can lead to significant differences in the intensity of seasons in one hemisphere versus the other, critically affecting the energy balance in regions where ice sheets might form or persist. Specifically, when the Northern Hemisphere experiences its summer at aphelion, as it does now, the summers are cooler, which is generally conducive to ice sheet growth as less winter snow melts. This cooling effect, especially at high latitudes, allows snow and ice to persist through the summer and accumulate over centuries and millennia. Now you might be pondering, these are such infinitesimally small, slow changes. Can they truly trigger an ice age? And the resounding answer is, yes, they absolutely can, especially when they combine their subtle influences in specific alignments, amplifying their effects. The true magic of the Milankovitch cycles lies in their intricate synergy. It's not one cycle alone, but the way their peaks and troughs coincide to create periods of sustained low solar insolation at critical times, particularly during Northern Hemisphere summers at high latitudes. For instance, a period of low eccentricity, more circular orbit but with a precessional alignment that puts Northern Hemisphere summer at aphelion, making those summers relatively cool, combined with a small axial tilt, milder seasons overall, meaning less intense summer sun at high latitudes, and a precessional alignment that results in cool Northern Hemisphere summers can create the ideal conditions for glaciation. Why cool Northern Hemisphere summers? Because that's when the winter snow has the chance to persist and accumulate year after year. If summers are too warm, even abundant winter snow will melt, preventing glacier growth, regardless of how much snow fell in winter. When the Milankovitch cycles conspire to deliver cool Northern Hemisphere summers, that unmelted snow steadily builds up, compresses into dense ice, and begins the slow, inexorable march of a glacier. Over thousands of years, those individual glaciers grow into colossal ice sheets that sprawl across continents, dramatically lowering global sea levels and transforming entire ecosystems. Why is the Northern Hemisphere so profoundly important in this intricate dance of climate? It's primarily because it possesses significantly more land at high latitudes than the Southern Hemisphere, and ice, to build up into those mile-thick behemoths that characterize a glacial period, requires solid land to accumulate upon. You simply cannot have a mile-thick glacier floating on the open ocean, at least not in the same vast, persistent and climate-altering way that land-based ice sheets do. While sea ice forms in the Southern Ocean around Antarctica, the vast Antarctic ice sheet itself is land-based. Therefore, the critical factor often boils down to the Northern Hemisphere's summer temperatures. If these summers are cool enough to prevent the complete melting of winter snowfall, then the stage is set for glaciation. These cycles, in their subtle yet powerful way, orchestrate the ebb and flow of Earth's grand icy chapters, pushing our planet between warmer interglacial periods and deeper, colder glacial maxima. They are the astronomical pacemakers of Earth's long-term climate, offering a profound glimpse into the delicate balance that governs our world. The scientific evidence for the Milankovitch theory is robust, supported by meticulous analysis of deep-sea sediment cores, which contain microfossils, like foraminifera, and isotopic records of past ocean temperatures and ice volume, particularly the oxygen isotope ratios, D18O, in their shells, which reflect both temperature and the global ice volume, and ice core data from Antarctica and Greenland, which preserve ancient atmospheric gases trapped in air bubbles, along with isotopic records of past temperature and precipitation from the ice itself. These records provide remarkably detailed paleoclimate archives spanning hundreds of thousands of years. They show clear correlations between these orbital variations and past climate changes, validating Milankovitch's brilliant calculations. The theory beautifully explains the approximately 100,000-year periodicity of glacial-interglacial cycles over the past million years, a dominant feature of the Quaternary Ice Age. This journey through Earth's icy past reveals a planet of incredible dynamism, constantly shifting and evolving under the influence of forces both terrestrial and cosmic. As we drift through these ancient rhythms of freeze and thaw, what new questions does this grand narrative spark in your mind? Perhaps you're wondering how these past climate changes compare to what we see today, or what other hidden stories the Earth's deep past might hold waiting for us to uncover. The exploration of these profound periods of Earth's history not only satisfies our scientific curiosity, but also provides invaluable context for understanding current and future climate shifts, reminding us of the planet's immense capacity for change and the intricate, often slow mechanisms that govern its climate.